So today we're going to start talking about the molar mass and percent composition. I know we've been over this in class a few times on some of our bell ringer work, but we're going to go through it today a little more in depth and talk about that. You'll also see a today's meet link in Edmodo, so if you would click on that as you go through the PowerPoint. Expectation is that you are taking notes, and we'll be by to check those notes to make sure you've got those. And then anything that you run into that you have questions with, something that needs a point of clarification, post that question on today's meet, and at the middle of the class I'll take some time and go over all of those questions that have been loaded onto today's meet. So let's try this as our first run through with this program. We'll see how it works and see what we can do. So let's start out here. Stoichiometry, ratios, combinations. Now I know that most of us have been through the stoichiometry portion where we're balancing equations, and the law of conservation of mass says that what's on the left side must also balance on the right side because we can't destroy or create elements. Same thing here when we get into mass composition. Let's go ahead and move forward. Molecular mass and formula masses. Molecular masses, sometimes called molecular weight. We've talked about these before. You may have seen them in grams. In particular cases of today's PowerPoint, you may also see it in AMUs, which is atomic mass unit. But the mass in AMUs is the individual molecule, and so you'll use your periodic table to tally those up. And you're going to multiply the atomic mass for each element in a molecule by the number or quantity of atoms of that element, and then total up your total masses. What we get then is a formula mass. The formula weight is the mass of an actual compound. So we're going to look at ionic compounds, but you could certainly do this for covalent compounds or ester type compounds as well. So here we go. Calculate the molar mass for carbon dioxide. Hopefully you know that's CO2 by now. Write down each element. You've got one carbon, which is a mass of 12. Came from your periodic table, so locate that. And then you've got two oxygens, which is 16, also from your periodic table. Gives you a total of 32. If we add both of these up, what you get is a total of 44.01 atomic mass units. And like I said, sometimes I went through and referred to it as grams, and you can certainly do that under certain circumstances, but for today we're going to use the AMU designation. So what I've got here is some for you to practice. These are not hard. Sulfur trioxide, you should be able to come up with that formula on your own, so I'm going to let you do that. Barium phosphate, silver nitrate, and then acetic acid. Acetic acid is commonly referred to as vinegar, and I think we've talked about that in the past as well. While you're calculating the first three, I will give you a moment to do that. And please put that in your notes, because I'm going to come by and check to make sure that you have those in your notes as well. And I'm going to go ahead and give you the formula for acetic acid right now. Acetic acid is CH3COOH. Again, that is CH3COOH. And that's all one formula. So that will be your acetic acid. So take a moment, go through and calculate these. What I'll do is post an exemplar with the answers to these on Edmodo so that you can have that to look at. Also, feel free to pause at this moment if you'd like to pause the video if you want a few moments to work these out. I'm going to go on with lecture, but again, all you have to do is hit the pause button and you can go forward from there. Percent composition. once you've calculated the atomic mass units, or the molar mass, as I call it, then we can take that and use that to calculate the percent composition of compounds. You calculate these by dividing your total mass of each element in the compound by the molecular mass of the compound of one of those. So for example, if you're doing carbon dioxide, you would take the percent of carbon that you have over the total weight of carbon dioxide and divide those and then multiply by 100, and that gives you the percent composition for carbon. Ideally, if you were to subtract that in this case, since there's only two elements, then you could come up with the other percentage of oxygen. It's a little more difficult when you have more than two elements. If you've got something with 3 or 4 or 5, a more complex molecule, then what you'll want to do is go through and set up each one of those to get your percent compositions. But these are critical in chemistry because it allows for verification of a purity of a sample. So we can take the number that we figure as being 100% reliable and compare that to what we do in the lab. So if we get a lab sample of CO2, we can see how pure it is and compare it against what the known percent composition of CO2 should be. So it's really handy in those situations. And here you've got your actual formula that you would use. You've got your percent mass of an element. You've got the atomic mass of the element on top, just that element, divided by your total formula or molecular mass, and then multiply by 100 to get your percentage. Again, feel free to pause here if you'd like that, so that you can get that into your notes. Percent composition, here's one that's done for you. Calculate the percent composition of iron in a sample of iron 3 oxide. You've got the formula, which is the F2O3, and then you're going to calculate the formula, or calculate the formula mass, and you're going to take that, and you've got 2 irons, if you notice. You're going to multiply those by 55.85. It's okay with me if you round to 56. That's not a big deal to me. To get 111.7 or 112 if you rounded. And then oxygen, you got 3 of those times 16 each. It gives you 48. If you add the 111.7 or the 112 plus 48, you should come up with the 159.7, or you may have got 160 if you rounded. What we're going to do with that then is take that 111 or 112 and divide it by the total of the 160 or the 159.7, and by doing that you can tell that iron is 69.9% right in this sample. So what is the percent of oxygen? Well, you can simply subtract 100 minus the 69.9, so roughly you would get close to 30% by doing your subtraction. You could definitely go through and do the same process for the oxygen. However, when there's only 2 elements, it's just as simple to subtract from the 100. So your turn. We're going to give you here, I want to know how much oxygen is in a sample of potassium chlorate. Now, chlorate's a polyatomic ion. You may have to go back and look that up in your polyatomic ion sheet. Feel free to do that. Again, feel free to pause here so you can get your work done. I'd really like to see that in your notebook as I come by and check your notes today to see these are done. Again, you may pause here if you need some time. Okay, the next part here is just some review from items that we've already accomplished in writing chemical equations, balancing chemical equations. In fact, what we can do with molar mass and percent composition is take those and make those in addition to. So you could balance your whole equation, and then I can concentrate on one specific product and ask you to come up with a percent composition for that particular product. So, and we'll have you doing some of those like in this slide here. Your product is NH4Cl. And you've got the word equation as well. It says ammonia reacts with hydrochloric acid to produce ammonium chloride. So I'd really like to see you go and tell me, give me all the percent comps for the product ammonium chloride. And again, put those into your notebooks. Feel free to pause if you need the time. But go through and set that up. Show your work. Always show your work. So I know if you went wrong, I can help you pinpoint where you went wrong. So you want to come up with molar mass and percent comp for ammonium chloride. As a third request for this one, I'd also like for you to tell me which one is the limiting reactant. In other words, which one is occurring in the lowest percentage. That one will be the one that element will be the one that you run out of first, which means that will limit how much ammonium chloride could be produced. So take a moment, go through, calculate those. Again, you're going to give me the molar mass of ammonium chloride. You're going to give me the percent comp of nitrogen, hydrogen, and chlorine in ammonium chloride. And then of those three elements, you're going to tell me which one is your limiting reactant. As just a brief reminder, anything that you have questions with or anything that's not clear, please post in today's meet so that I can come by and go over those as a class set and respond to those. Just a quick reminder here, reactants, products, and symbols. We've covered this before. This is not new. This is just review. Reactants are typically on the left side of the arrow, and products are what's being formed. It's on the right side of the arrow. Also, you've got your symbols, solid, liquids, gases, and aqueous, which means they can be broken down by water. Balancing equations, this is where we're going to stop in this particular PowerPoint. It carries on through material which we've already covered. Please make note of stopping on slide 12 here. Make sure you've got all of your notes and all of your practice problems set up and solved before I come check your notes for this section. Your next assignment will be on Edmodo. So once you've completed this and you've got all your notes taken, go to Edmodo, log on. There'll be an assignment waiting for you with more practice problems for percent comp and molar mass and limiting reactants. Again, just a reminder, today's meet, post any questions you have so that we can reference those and take care of those as a group. Also, give me any feedback as to how you liked this approach for notes, anything that you'd like to see modified as well. Thank you.